Hi everyone, my name is Lan. I am a postdoc researcher at NC State University. Today I'm going to talk about the carbon and energy applications of fast pyrolysis biorefineries with blended feedstocks and decentralized supply chain design in the Southeastern United States. Biofuel has grown fast as providing benefits in the environmental aspect and the energy security. And the left picture I show here is the global biofuel production, historical data, and the forecasting data provided by IEA, International Energy Agency, which there is still an increase to 2030. The traditional biorefinery system always adopted a centralized design with a single type of feedstocks, which can be vulnerable to the variations in feedstock cost, quality, and availability. For second-generation biofuel production from the lignocellulosic biomass, two possible methods can be helpful to minimize these risks from the literature. The first one is using blended biomass feedstocks. The second one is adopting decentralized pre-processing facilities. The southeastern U.S. is a region rich of forest residue and switchgrass, as shown in the pictures above, published by the DOE Billington report. The left one is for logging residue, and the right one is for switchgrass yield. Hence, in this study, we choose the forest residues and the switchgrass as our two biomass feedstocks. To convert the biomass to biofuel, fast pyrolysis has been a great choice to produce a suite of fuel products from a wide variety of biomass feedstocks. According to the literature search, the knowledge gap existing in quantifying the environmental implications of using blended biomass and the decentralized pre-processing sites, or so-called depots. And in the quantifying the impacts of varied system configurations, facility capacities, blending ratios, and the pre-processing technologies. To quantify the environmental implications, we can use LCA. And for the environmental impact indicators in this study, we use the commonly used primary energy consumption and GWP. To address this gap that I mentioned in previous slides, we developed a cradle-to-gate LCA model for fast pyrolysis biofuel production using pine residues and switchgrass. We compared two different system configurations, traditional centralized configuration and the decentralized configuration. For decentralized configuration, the biomass feedstocks will be firstly sent to the depot by initial transportation. Then at the depot, we pre-process the feedstocks to produce pellets. Then the pellets are sent to the biorefinery by secondary transportation to produce biofuel. If this is the traditional configuration, then the depot in this dashed line box can be skipped. Now, let's look at our study approach. First, we collected data from the literature database manufacturer to build the process model for depot pre-processing. And then with our previously experimental work, we built the simulation model for biorefinery processing in Aspen Plus, which I will introduce later. Then we built the cradle-to-gate LCA model. Finally, we conducted scenario analysis to fully understand the impacts of varied system configurations, blending ratios, pre-processing technologies, depot capacity, biorefinery capacity. Now, let's look at the stages one by one. For pine residue production, the residues are generated from commercial thinning and logging. The rotation period we assume is 25 years. To get the LCA data, we collected the data from the literature. We included the upstream burdens of providing chemicals and fuels used in this stage. After the residues are generated, they will be shipped on site and then transported. Notice that we assume in this study the output logs are still on their bulk. For switchgrass, the rotation period we assume is 10 years. At the first year, we will do the site preparation and planting. Then every year we will do harvesting. The environmental burdens of the site preparation and planting will be evenly allocated to the following years. After the harvesting, the switchgrass will be collected to make bales before transportation. After feedstocks are sent to the depot, we explore two different pathways. One is called CPP, conventional pelleting process. The other one is called HMPP, high moisture pelleting process, where we alternate the order of the unit operations. For CPP, this one, the first unit operation is initial grinding. For switchgrass, we use a bale grinder. As pine residues have been chipped on forest side, so initial grinding has already been performed. So if we use a 100% residue, we don't need the bale grinder. Then we dry the feedstocks in the rotary dryer to lower the moisture content to 12%. Then do the secondary grinding in the hammer mill. After that, we do the densification to make the pellets in the pellet mill. And the final pellet's moisture content is 9%. For HMPP, after pre-drying for pine residues, we do the initial and the secondary grinding. If the feedstocks have been small enough after the initial grinding, they can pass the secondary grinding and goes to the pellet mill. Then we do the densification and dry the pellets in the grain dryer. We build the thermodynamic models for dryers and collected the data for the other unit operations from the literature. For biorefinery, we built the simulation model in Aspen Plus based on our previous years of experimental work. We are able to quantify the impact of biomass compensations, namely the moisture content, carbon content, and ash content. After the feedstock pre-treatment, we do the fast process for a few seconds. Then we separate the pyrolytic vapor from the solids. Then we do the bio-oil recovery and use the hydrogen from the steam reforming to upgrade the bio-oil. We can get the final products as the gasoline range and diesel range products. All the biochar and off-gas in this study are burned in the CHP plant to produce heat and power. Since our products, including the diesel, gasoline, and the byproducts electricity, so in this study, we built a scenario analysis including two different scenarios based on different allocation methods. In scenario 1, we use energy allocation. And in scenario 2, we use a system expansion for the surplus electricity, or say we consider the electricity credits. The depot capacity we are looking at is 250 and 500 ODT per day. ODT per day means oven dry metric ton per day. And we are looking at 1,000, 1,500, and 2,000, three different biorefinery capacities. And the blending ratio, we are looking at four different blending ratios, which blends the pine residue from 100% to 25%. Here I show the results for the life cycle primary energy consumption by using energy allocation method in scenario 1, because we have our main product biofuel and the byproduct electricity from the CHP plant. Here I only show a example for 250 ODT per day depot and the 2000 ODT per day biorefinery. The reason is that we found the changing the facility capacities has minor impacts on our results. The x-axis here is the pine residue fraction. In the feedstock, we have totally 4 different blending ratios. The left bars are for no depot case. Middle bars are CPP case. The right bars are HMPP case. If we look at the total numbers, we can have 2 observations. One is using depot will increase the primary energy consumption. The other one is if we increase the switchgrass blending ratio from the left to right, the total energy consumption will decrease. This is because of the low moisture content of switchgrass. If we look at the details, the bottom dark blue bar is the biorefinery processing, which is the dominant part, and the yellow part on the top stands for the depot pre-processing, which is the second large part. If we increase the switchgrass blending ratio, the yellow bars decrease significantly because you consume less energy in drying. The transportation in gray bars accounts very minor portion, 2 to 5%. The rest is biomass production. If we use the same allocation method and look at the GWP, we can see all the results are very similar. That is because the GWP there are mainly due to fossil fuel consumption. If we change the allocation method from energy allocation to system expansion, we can have this figure. The absolute value decreases as we change the allocation method, but all the training is the same. If we look at the 2.25 pine residue fraction, no depot and HMPP depot, as I showed in the dashed line box here, the results are very similar. That means 75% switchgrass blending with HMPP depot can compete with the baseline case. Then let's look at an example of a 250 ODT per day CPP depot with a 50-50 blending ratio. Here the pine residue moisture content is the most dominant one because of the high moisture content. If we further look at the parameters, those related to rotary drying are among the top ones because drying is the most energy consuming part. Then here I show a fossil GHG and the biogenic GHG results for scenario 2. The gray bar are fossil GHG emissions, while the light green bars are biogenic GHG emissions. The biogenic GHG emissions are mostly released in the biorefinery where we burn all the biochar and off gas. The dark green bar are biogenic carbon stored in the fuel, which are negative values. The blue bars in dashed line stand for the electricity credits you can get. Compared to the fossil GHG emissions, biogenic GHG emissions are actually larger than the fossil-based GHG emissions. To summarize, this study examines the impact of various system configuration, blending ratios, pre-processing technologies, depot capacity, and biorefinery capacity on primary energy consumption and the GWP. First, HMPP shows advantages in the energy consumption and the GWP. Second, increasing capacity has minor impacts on energy consumption and the GWP. Third, transportation is a small part for LCA results. Lastly, increasing switchgrass in blending ratio can reduce the environmental impacts. And this work has been published in the Energy Technology last year. Finally, I want to thank our funding agency for supporting this work. And thank you all for your attention.